Welcome back, this is Professor Xiaoma. In this video, I will demonstrate and explain a specific hands-on problem. Now keep in mind that in demonstrating the hands-on problem, I will use an example data set, which is default 1. When you do the homework, the data set is different, so make sure that you adapt the code to work with the homework. In the video, I assume that whatever Python package that we will be using, you have already installed them. If you realize that you haven't installed a specific package and you need to install it in the middle of the video, simply pause the video and go ahead and install it. Install the Python package by following the tutorials that I uploaded. Now let's get started. For this demo, I'm still using the default 1 dataset as is used in many of the other homework videos. Previously in part 1, we completed the steps in one full iteration of the for loop. We obtained the new weights as compared to the old weights as printed here. Next, we will put the for loop together and run the for loop. Before I put the for loop together, let me copy the codes for initialization so that you can replicate the results. So here are the codes. These are exactly the same as the initialization cell that I run in the previous video. To put together the for loop, you would simply copy the codes in each of the steps of the one iteration of the for loop, beginning from the net input function. So you would put these codes, but not the printing codes. You will put these codes inside the loop with proper notation. So here it goes. First of all, before the for loop, you would need an empty list to store the cost values in order to look at the trajectory of the cost values. Inside the for loop, these are the same codes that were run before. The decision process includes the net input. The activation process includes the activation function and calculating the adaptive error. The optimization process includes calculating the gradient, calculate the weight update, and then update the weight. And finally, within the loop, this is new here. To trace the trajectory of the cost function, we need to compute the cost in each epoch. For Adaline model, the cost is simply sum of squared errors. And as you are perhaps familiar now, sum of squared errors can be implemented in Python using the dot function. And by multiplying two errors together, divide that by 2. Now you get the cost. Once you get the cost for this epoch, make sure to append that cost value into values list that you created. And in the end, you will have the number of epochs of the cost values stored in the list. Now let's run this. Now let's review the cost values. So I will print all the cost values, and there are 10 of them because I had set 10 as epochs, and I will round all the values to 3 decimals. Let's run this. You should get the same values. Now closely observe these values. The first one is 9.3. The second one is already 5.6 times 10 to the 4. And the exponent is increasing over time. So this means that the cost value is exploding. Because we are supposed to reduce and minimize the cost values, the exploding cost value means that we are not improving the model. We are actually making it worse. But this happens a lot. The reason behind this is most likely that the learning curve eta is too large. You end up going up the spiral rather than going down the curve. So we need to reduce the eta. In improving eta, normally you would reduce the size of eta by a factor of 10. For instance, observe the current value of eta is 0.01. So the next one you try is 0.001, reduced by a factor of 10. So let's rerun and retrain the model with a new eta. As with earlier, before you retrain the model, make sure you reinitialize the starting values. After a few trials, the ADA of 0.0002 seems to be reasonable, so I'm going to run this and demonstrate the results here. So this echoes something that is said in the first video. Why does ADA, the learning rate, has to be very small? Because if it's not small enough, the cost function will explode. So run this, the same initial weights, except for the ADA learning rate. Now here are the exact same codes for the for loop, and run this. And now let's look at the cost values. Run this again. Now look at the cost values. The values begin with 93.7 and it gradually decreases to 31. So this is a good sign. With learning rate of 0.0002, the model seems to be on a good trajectory. Now let's make a plot of the cost value to see more clearly about the trajectory. So here, I'm going to make a plot with subplot 1 by 1, so there's only one plot. I'm going to plot the line and the points of the cost trajectory, and I put on the labels here. Now run the... Alright, it looks like the model is learning. In the first few epochs, cost values drop significantly. As model trains more, cost values still decrease, but the speed of decrease is slowing. You can see the curve. So now with this graph, the model will be almost ready if we train it a little bit more. So let's do that. Let's restart the training process. And with earlier, let's reinitialize the starting values with the small ADA. So now I put the initialization codes and the for loop codes together. As you can see here, I use a small ADA. So I use a larger value for the epochs, which means the learning will run for 20 iterations. Let's run this. And let's review the values by making the plot again with the new cost values. Copy the codes here. Essentially the same codes. I added one more line to rearrange the tick marks on the x-axis. Let's run this. Okay, now with 20 epochs, the cost curve is really bending over and it's flattening. I think the model has been trained adequately. Let us evaluate the accuracy of the model. Model accuracy basically computes percentage of the correct prediction of the trained model by comparing the predicted label of the target variable with the actual value of the target variable. But here is a caveat. Because we did not apply train test split to the data, we used the entire data as a training set. And because the model is trained using the training set, its performance is likely to be high when predicting the labels of the training set, because that's the data that the model learned. To evaluate model accuracy, we need to calculate the predicted values and the predicted label from scratch. We will implement this using Python's NumPy. So here are the codes. Let me talk about these codes. Basically, making a prediction is similar to doing one run of the forward propagation process of the Adaline model. We will only need to implement the decision process where you calculate the net input. That's the first line here. These codes are the same with the codes in the for loop. And next, you will apply the activation. And with the activated values, you are now ready to make the prediction. You do not have to go forward and calculate the rest, including calculating the error and the optimization process. You do not have to do those. With the activated value, apply an intuitive threshold value of 0.5 to label the prediction. If the activated value is larger than 0.05, the prediction is yes, the customer defaulted. If the activated value is smaller than 0.5, the predicted value of the target is no default. In the end, YPred is an array or a series with n by 1 dimension. Now run this code. with the predicted y and we have the original y, we can compare their differences and calculate the model accuracy. Now here are the codes. In calculating the model accuracy, I'm using a utility here. I'm using a function accuracy score from scikit-learn to quickly calculate the accuracy. Basically, the function compares the overlap and differences between each element of that dimension of the y versus y predicted and returns a value of the accuracy. And with that accuracy and with the total sample size as n, I calculated the number of correct hits and the number of incorrect predictions, and then I formatted the values including the accuracy and print the results. Now let's run this. So the trained Adaline model made almost 1,000, which is the sample size. It made 982 correct predictions or classification and only made 18 mistakes on the trained data. The accuracy is 0.982, which is 98.2%. This is very good model, almost perfect model. However, you know the caveat, the model may be overfit to the data. We will talk about overfit and how to deal with it in the next videos. So by now, the Adaline model implementation demo is finished. Hope you enjoyed this video. See you next time.